Right on the next topic, electromagnetic induction. Electromagnetic induction. Okay, listen here. So in magnetism and matter and moving charges and magnetism, we were learning about the current, so or the charge. So when the charge is moving, the magnetic field has been produced. So in this lesson we are talking about when the magnetic field is moving, the charge is produced. Okay, write down first point. In moving charges and magnetism, and magnetism and matter, when we take a conductor, and if a charge flows in a conductor, due to that both electric field and magnetic field forms. Both electric field and magnetic field forms. The next point, in electromagnetic induction it is reversed. In electromagnetic induction, that is in EMI, it is reversed process. Right on the next point, when a magnetic field is varied, due to that a current is produced. Due to that a current is produced, and this current is called as induced current. Okay, so whatever the charges are flowing around the appliances is a normal charge, but when we are talking about a magnetic field, due to the magnetic field a current is produced, that current is called as induced current. So in that we are not using any kind of battery or any kind of appliances, but without using the batteries and appliances we are getting the current, that current is called as induced current. Any doubt in this? So how we are getting is like varying of the magnetic field. When I talk about for example, this is my conductor, so some magnetic fields are flowing like this. If I take my conductor left and right, will the magnetic field changes? Like, let me talk about how many field lines are here. 6 field lines. Okay, if I take this the ring, the conductor to left and right, will the magnetic field changes? No. So I need to change the magnetic field. Either I can take top and bottom, no. From top to bottom, if I try to swing, obviously magnetic field change. If I take this to the top, no, only one magnetic field will be there. When it comes to the center, every magnetic field will be there. When it goes to the bottom, again one or two magnetic field will be there. So obviously in this case I can say that the magnetic field lines are changing. Yes or no? So when the magnetic fields are changing, the current is produced. That current is called as induced current. So this one will see in the Faraday's law. Okay. And the first topic under electromagnetic induction is magnetic flux. Magnetic flux. So what is the meaning of electric flux? We were talking in electric charges and fields. What is the meaning of flux? A flow of something. So electric flux is nothing but electric field is flowing. So now we are talking about the magnetic flux. So flow of something is nothing but flux, but we are talking about the magnetic flux. So obviously magnetic field lines are flowing. Okay, write down the first point. Flux is defined as the magnetic field lines passing through a cross section area, So obviously we were talking in electric flux also. Electric field lines are passing through a area of the cross section we were talking. And what was the formula of the electric flux? Phi is equals to E dot ds or Es cos theta, like electric field into area into the angle between them. Similarly here, phi is equals to Ba cos theta. B is nothing but the magnetic field. Phi is equals to B dot A. Phi is equals to B dot A. So both are a vector quantity, but when we get as a result, it is a scalar quantity. Cos theta, right? So cos theta, where we are using in first year, the work energy and power. Yes, no? Force is a vector quantity, displacement is a vector quantity, but the resultant product is a scalar. So similarly, magnetic field and area is a vector quantity, but the resultant will be a scalar. Okay, write down. It is a scalar property. It is a scalar property. The next point is area is a vector quantity. Area is a vector quantity. Area is a vector quantity, and it is directed radially outward, and it is directed radially outward. So radially outward in the sense, if I talk about this is my field, so this is my area of the cross section, like it is radially outward, radially outward. So what is theta here? It is the angle between magnetic field and area of the cross section. Okay, now if I'll give a condition, give me answer for these questions. This is my area and this is my magnetic field. This is my area, this is my magnetic field, and this area and this magnetic field, and this is the angle theta. Can you give answer for these three cases? Which one? First one is phi is equals to 0. Any doubt here? Because the angle between them is cos 90, 0. So something multiplied by 0, I will get 0. What about the second one? Phi is equals to B A, because the angle between them is 0 degree. So cos 0 is 1. So phi is equals to B A. What about this one? B A 90 minus theta. Right. Let others also think. What is the answer for this case? B A sin theta. Correct? Everyone? Anyone having any doubt in this? Why we are taking B A sin theta? Because we are talking about the angle between these two things. Okay, they have given the angle with respect to horizontal, that is theta, but we need to know the angle between these two things. The total angle is 90, so this is 90 minus theta. So phi will be equals to B A cos of 90 minus theta. So cos, no, so and this is 90, so 90 means it will be sine. And what about 90 minus theta? First quadrant, no, everything is positive, so theta. So B A sin theta phi. Take down, these are the three cases. Suppose the fourth case, if I give like this, this is A and this is B, minus B A, because it is anti-parallel and angle is 180 degree, cos 180 is minus 1, so minus B A. Completed? Completed. Right on the next point, the SI unit of magnetic flux is, the SI unit of magnetic flux is, SI unit of magnetic flux is Weber. So WB, Weber. SI unit is Weber. The next point, the CGS unit, CGS unit is Maxwell. CGS unit is Maxwell. CGS unit is Maxwell. Maxwell. Right on the next point, 1 Weber is equals to 1 Weber is equals to 10 power 8 Maxwell. 1 Weber is equals to 10 power 8 Maxwell. Then 1 Maxwell will be equals to 10 power minus 8. So any doubt in the first topic, magnetic flux? Right on the next topic, Faraday's law. Faraday's law. Faraday's law. Now we will talk about the thing. So initially I have talked about the ring, no, the conductor, so which I have taken to magnetic field, and if I try to move left or right or top or bottom, okay, so where the current is produced, that current is called as induced current. So this is the experiment done by the Faraday's, and by this he got the induced current. Write down. The change in magnetic flux induces a EMF, induces an EMF. What is EMF? So induces an EMF in a conductor. In bracket you can make it like as well as current in bracket. Okay, now I will give two conditions. So what is this cross mark denotes? Magnetic field inside the board, paper. Okay, so I'll take a conductor. I'll try to move this conductor in this way, and I'll take one more conductor. So this is my axis. I'll try to rotate this conductor like this. I'll try to rotate the conductor. Two conditions I have given, in which the current flows and which the current doesn't flow. This one I am rotating like this. So magnetic fields are flowing like this. I am taking the conductor, I am rotating like this. And the second one, first one is conductor I have taken, I have moved like this. Think carefully. Second one, current flows. Obviously if I talk about this is my conductor and magnetic field lines are flowing like this. So if I try to rotate like this, obviously the area is reducing, no? Again if I try to rotate like this, area has been increased. So when the area increases, the magnetic field lines which is passing through the area also increases. So from the first condition I can say that there is no induced current. From the second condition I can say that induced current is produced. Take down. So why there is no induced current here? Because of uniform magnetic field. Uniform in the sense it will be constant. Take your pen and draw, madam. Don't wait for the pencils. So E is nothing but rate of change of magnetic flux. So rate of change of nothing but it is with respect to time we are talking. So d phi by dt. But I am opposing the magnetic flux, no, like I am going against the magnetic flux. If magnetic flux is flowing like this, I am taking and moving like this, going in front, I am coming back again. So which means I am opposing and getting the magnetic, like induced current or induced EMF. So that denotes the negative symbol. So negative symbols denotes opposing the magnetic flux and getting the induced EMF. Right now, so only up to E is equals to d phi by dt has been given by Faraday's. Okay, this negative symbol, which means the direction, has been given by Lenz. Okay, Lenz law. The direction is given by Lenz. So Lenz is a scientist. So you have given the direction like positive or negative or north pole or south pole, like this. Okay, we will talk about that. So how I will get the current now? Like when I am moving the magnetic, like the conductor, the change in magnetic flux taken place, due to that induced EMF is produced. But when I connect the conductor with a galvanometer, I can see the fluctuation of the current. Okay, galvanometer gives the fluctuation of the current. So suppose if I talk about, there is a conductor which has been connected with a galvanometer. Okay, galvanometer. Now I will take a magnet. So this is my north pole and this is my south pole. Okay, north pole and south pole. Now if I try to move this magnet, will a current is induced or not? If I try to move this magnet front and back, will the current is induced or not? How and why? How and why? Magnetic flux changes. Is magnetic flux is changing? EMF is produced. How the EMF is produced? Okay, so think that when we are talking about the charges, positive or negative, there is a field lines, the imaginary lines we were talking, no? Obviously when we talk about a north pole or south pole, like a positive pole and negative pole, no? Obviously in this also magnetic field lines will be there. There electric field lines, here magnetic field lines. So if I take the magnetic field lines for example, if I try to go near to the conductor, the number of field lines passing the conductor will be more. When I take away from the conductor, the number of field lines passing the conductor will be less. So I can say that due to the change in magnetic field lines, okay, this is magnetic field lines, this is area. When I pass this magnetic field lines in this area, flux is produced. Getting the point? Understood? It is not magnetic flux. This is magnetic field line taking into area of a conductor A, and due to this change I am getting the induced current. Okay, getting what is the meaning of magnetic flux? when a field line passing through the cross section area A, right? Field lines passing through the cross section area A, flux is produced, but change in flux is produced induced current or induced EMF. Okay, when I need to find what is the direction of the current when they have given north pole or south pole, so if I take north pole, take the N as it is. Okay, obviously current is produced in this, so if I want to know what is the direction of the current, if I take the cell, I can say the direction of the current, no? Yes or no? Here cell is not there, but induced current has been produced due to magnetic flux, change in magnetic flux. So whatever pole is there, take the symbol as it is and denote the arrow mark like this. So this is my direction of the current. Okay, if I take the south pole, so it will be anti-clockwise direction. So take like this. So it is anti-clockwise direction. So when south pole is there, it's an anti-clockwise current is produced. When north pole is there, it's a, it is anti-clockwise and that is clockwise. Okay. So for south pole it is a clockwise and north pole it is anti-clockwise. Getting? First you can draw the diagram for the north pole, then you can take the south pole diagram. Only you take the symbol and see the direction of the current. Okay, for finding the direction. And listen 1 minute. So how do I know this is my north pole or this is my south pole? When I go near to the object, I will get a south pole. Attraction will take place. North pole and south pole. When I go away from the object, the conductor, it's a north pole. Like opposite, no? When I am going away, so obviously both are in opposite. Both are in same, sorry. When I go away, both are in same. When I come near to the point, both are same poles. Okay, listen. So if this is my galvanometer and I have taken the magnet here, north pole and south pole. Now I have taken the one more magnet here, north pole and south pole, two conditions. So which is near magnet? This one. So if this is near to the conductor, obviously the conductor should be a south. Yes, no, it will be get attracted. If it is away means obviously it will be a north. Understood? That's the point I have told you. So obviously if it is near, it should be south and the direction will be in clockwise. Completed. So there is one more condition in this case. If I take the conductor which has been connected with a galvanometer. Now the magnet is there, either it can be north pole or south pole or north pole, whatever it is. If I try to rotate the magnet like this I am rotating, will there be any magnetic flux will produced? Will there any magnetic flux will be produced, or any field line will be changes? Field line produces, yes or no? Field line is produced, okay, and obviously it is passing the conductor also. But if I try to rotate the magnet like this, I am not taking the magnet in this direction, okay, I am rotating magnet, like I am just rotating, which means the north pole remains as it is and south pole also remains as it is in the same place, and just is rotating like this, which means there is no field line changes in the conductor, which means there is no flux changes. So obviously induced current will be 0. Induced current will be 0. Take the third condition. Completed? Okay, listen, the next condition, I will just remove the galvanometer here. Now will there be any current produced here? Why? Galvanometer ledu, and one more thing, it's an open circuit, no, there will not be any way to pass the current from the wire, yes, no. So the next topic is open loop. Open loop. Open loop. First point is no battery or no cell has been connected. No battery or no cell has been connected, including galvanometer. No battery, no cell has been connected, including galvanometer. Okay. Now I have taken the magnet north pole and south pole. I am trying to move the magnet left and right, which means obviously change in magnetic flux has been produced. Will there be any EMF is produced? Will there be any EMF will be produced here? No. Write down. Due to change in flux, EMF is produced or induced. Due to closed, because of closed, I mean because of open, no current will be there, that's it. Induced EMF will be there. But because of that, I can say that there has been a cell, either it can be a positive or negative cell. due to that. EMF unnadi, if I try to connect, obviously current will flow, no? Yes or no? If EMF is not there, if I try to connect also, there is no use, no? Getting the point? EMF is already there for the open loop. If I try to connect with the open loop, the galvanometer, then I can feel the current. If I say the point for the open loop also EMF is not there, if I, and the second point, if I try to connect the galvanometer here, obviously there is no current, no? Understood the point? So the first point is, even if it is a open loop, due to change in flux, EMF is induced. Due to change in flux, EMF is induced. But induced current is 0. But induced current is 0. Because there is no path to flow. Because there is no path to flow. Okay. So I am getting near to the conductor. If we take condition, if I get near to the conductor, what will be the pole here? I am coming near to the conductor, right? So this is my direction, no? Okay. If this is my direction, from where the current is going, it's coming like this, no? So there will be a cell. So obviously which one will be negative and which one will be positive? So this is my negative and this is my positive. From negative, electron is flowing to the positive side. Okay, electron I am talking. So this is my direction and this is my cell. If they are asking what is the symbol of the cells, negative, positive or positive, negative, this is my answer. So negative and positive, and I have taken the south pole because it is near to the conductor. If I go away from the conductor, then it will be a north pole. So this is my direction, which means it will be in this direction, no, anti-clockwise direction. This is my negative and this is my positive. Take down. Why we are finding the current direction means, if I try to connect the galvanometer, I need to know the current direction, no? So this is my current direction. Once you can refer the notes, whatever we have seen now, first we'll go for the question. there is a conductor. Okay, they have given the conductor is north pole. North pole. Now in this conductor they have dropped a magnet. This is north pole and this is south pole. Okay, they have dropped the magnet and it is going with an acceleration a, for example, will keep going with an acceleration a. So obviously if I drop the magnet, it will cross the conductor and it will go no like this. This is my north pole and this is my south pole. Yes or no? There is a conductor, I have dropped like this, which means it will pass the conductor and it will go down. Okay. Now the options are, is A is greater than G, option B is A is less than G, or option C is A is equals to G. Analyze it. Okay, what, why? Free body, yeah. A is less than G, A is greater than G, or A is equals to G. I need a proper explanation for this. Why? Acceleration. Initial velocity, it's going with a constant acceleration, I told. Acceleration is constant. I am talking about only acceleration and the gravity. I am not talking about any other thing, velocity, displacement, those kind of things I am not talking. Negative gravitation. A is equals to G. Why? అది కూడా డౌన్వర్డ్ కే మూవ్ అవుతుంది. ఐఎమ్ టాకింగ్ అబౌట్ ది యాక్సిలరేషన్ ఆఫ్ దిస్ వన్ విల్ ఇట్ బి ఈక్వల్ టు గ్రావిటీ ఆర్ ఇట్ విల్ బి లెస్ దెన్ గ్రావిటీ. ఐఎమ్ టాకింగ్. The question is, there is a conductor, I have taken a magnet, just dropped inside the conductor. Now I am talking about this this conductor is this magnet is going with an acceleration A. Is this acceleration is greater than G or less than G or equal to G? I am talking. Okay.
So maybe attraction comes.
Okay. Then.
So acceleration is less than.
Tell. Think. Completed your thinking? And whatever Bhumika has been told is correct. Okay. So since it is a north pole and this is a north pole, it is coming down, but it will try to oppose the acceleration. Yes or no? Obviously the acceleration will be less than G. When it is going down, it is a north pole and this is a south pole. It will try to attract it again. Obviously again here it is less than G and the option is B. Understood? Understood the point? Since it's a north pole and this is a north pole, it is coming down, but it should cross it and it should go. But in this point, it will try to oppose each other. Okay? Obviously, like acceleration will be less than gravity. Again, when it comes to here, it is not falling freely. It will try to attract. Okay? South pole and north pole, no? It will attract. Again, the acceleration will decreases. Okay, take down. Suppose the question is opposite. If this is a south, obviously it is greater than G because it will try to attract it. Again here try to repel, which means it will try to oppose it. It will go fast. So write the conditions also, why it is less than G also. Write down note point. So what was the EMF we are talking here? E is equals to minus d phi by E is equals to minus d phi by dt. What is the flux we are talking here? BA cos theta, no? We know that flux is equals to BA cos theta. So I can say that E is equals to minus d by dt of BA cos theta. This is my formula for the EMF. Suppose if it is a one conductor, I can take BA cos theta. If there is a n number of turns, then it is n into BA cos theta. N denotes the number of turns. Okay. So from this only we can derive the formula if anything is changing. For example, if magnetic field is changing, okay. For example, if magnetic field is changing means E is equals to only magnetic field changes, no, the remaining things will be constant. So minus A cos theta into dB by dt. This is only magnetic field changes. If suppose angle changes, E is equals to minus B A into d cos theta by dt or d theta by dt. Okay. So according to whatever the situation or question they are giving, okay, if magnetic field changes, only take dB by dt. Remaining things are constant, take it outside. Okay. If theta is changing, only take d theta by dt. The remaining things is constant. Keep it as it is. Take down. So this is for instantaneous, no, like d by dt is nothing but instantaneous, which we are talking about in straight lines also. Suppose it is a change like average, in the sense what I will take, minus delta phi by delta t. Yes, no, what is delta in the sense the change, 2 minus 1, the final minus initial. So it is minus of phi 2 minus phi 1 by delta t, which gives phi 1 minus phi 2 by delta t. This is another formula. E is equals to d phi by dt is one formula, delta phi by delta t is another formula. For average we will take, no, for average time t1 to t2. This is at time t1. Okay. At the time t1 in the sense instantaneous we are talking, time t1 to t2 in the sense the average we are talking. So now we have completed the Faraday's law and Lenz law, and some applications also we have completed. Now we will go for the motional EMF. Completed? Write down first. Yes, what happened? Which one? Which one? This one. So in this, no, like instantaneous means what? Like at that time we will talk. Like for example, at time t1 in the sense we'll use this formula. Okay. For example, from this is at, okay, at t1, from t1 is t is equals to 1 to t is equals to 2. Like in between I am talking. If I am talking about in between, I will use this formula. Okay. The average we will talk, like change in velocity we will say, no, similar to that. Completed? Okay. The next topic is Motional EMF. Motional EMF. Okay. Try to listen carefully here. I am taking the magnetic field. So there is a magnetic field B into the board. Now I am taking a conductor or a metal piece. Okay, metal piece. This is fixed here. Okay, this is fixed metal piece is there. Upon this, what I am doing is I am keeping one more a metal rod which is of P and Q, length L. Okay, length L. What I am doing is, this is a movable rod, this is a fixed metal piece and this is a movable rod. What I am doing is I am trying to pull towards right. I am trying to pull towards right. What happens here? It is cutting the magnetic field lines, no? It is cutting the magnetic field lines, no? If magnetic field lines are going inside, if I try to pull something like this, obviously it is cutting everything and coming near to me. Getting the point? The field lines are going inside. Here the metal piece has been fixed. Now there is a movable rod is there, like which I kept upon the metal piece. If I try to pull towards me, it will cut everything, whatever the field lines are going. If this is my field lines, something I am pulling towards me, it will cut and come, no? Yes or no? Obviously I can say that there is change in magnetic flux. Yes or no? Change in magnetic flux. Write down. Take the diagram first and let me tell the point, and I will tell you the formula also for this. Completed? When we try to move the rod, this also, this is a fixed rod and this is a movable rod. Okay. When we try to move the rod with a velocity v, it creates the change in flux. It creates the change in flux. So if I take the first point, it is cutting this line. If I coming in this between, there is no field lines are passing, which means 0. Again field lines are passing, so it will cut the field lines. Again 0. Again it will cut. Again 0. So which means it's keep on changing, right? So what is the point I have told? When we try to, okay, with the velocity v, it creates change in flux. Write down. Due to this, induced EMF is produced. Yes or no? If change in flux is there, induced EMF will be there, no? Due to this, induced EMF is produced. Due to this, induced EMF is produced. This EMF is called as motional EMF. This EMF is called as motional EMF. Understood the points? So induced EMF, induced current, motional EMF, getting the points. Why we are calling this as particularly induced or motional? Due to this motion, I am getting the motional EMF. Okay. So EMF E is equals to, what other things are available? Magnetic field is available, length is available, velocity is available. Okay, and it is BLV sin theta is the formula for the EMF. BLV sin theta. So listen, sin theta we are getting, but how we are getting in the sense, obviously the cross product, right? Now dot product is a cos theta, dot product, I mean a cross product is a sin theta. So is length changes? Length is a magnitude, only magnitude, no? But magnetic field and velocity is a vector quantity. So can I write like this? E is equals to L times V cross B. V cross B. This is my formula. L times V cross B. Done. Direction analysis for this. Okay. So for the Faraday's law and Lenz law also we have talked about the direction, no? Yes or no? The direction of the current, either clockwise or anti-clockwise. So for this direction analysis. Direction analysis. Under this topic, the directional analysis. So in this we use Fleming's right hand rule. Fleming's right hand rule. Fleming's right hand rule. What was left hand rule? FMC. Remember, force, magnetic field and the current velocity, right? No, or charge velocity. Now we are using the right hand rule. Okay, here we will use CBI. I will tell. Thumb finger denotes the conductor's velocity. Which conductor I am talking? The movable conductor. The conductor's velocity, thumb finger. So next is B, which means magnetic field lines. B is magnetic field lines, no? B is magnetic field lines, which is the index finger. Index finger denotes the magnetic field lines. Done. And what is the last one? I. So the center finger denotes the current direction. Induced current, okay? It is not a current, induced current direction. Induced current direction. So can we analyze the direction for this one now? So magnetic field is inside the field, velocity is this side, which means this is my magnetic field, this is my velocity direction, and this is my current direction. Try to analyze it. Thumb finger, velocity. This one, magnetic field lines, and the center finger, induced current. How the magnetic field lines is there first? It is inside, and which side it is velocity? This side, and the finger shows means the upward direction. So this is this is the direction of the current. Getting the point? You can take the direction of this. So for the diagram, the direction of the current is towards up. So in moving charges and magnetism, we are using the left hand thumb rule, which is FMC. Here it is CBI. Okay, CBI. Okay, now the thing is, current is flowing in this direction. What is the flow of electron? If they are asking, opposite direction, no? So this is my flow of current, and this is my flow of electrons. Electric field and electrons will be in opposite direction. That is the first point we were talking in the current electricity. So electrons always flows in the opposite direction of the current. Okay, with this I will stop for the class, and we will continue in the evening class. Okay, so any doubts?